Welcome to today's Engineers Newsletter Live program. I'm Jeannie Harshaw from Trane System and Application Engineering Group, and today we'll be discussing variable speed drives on compressors. As always, a little housekeeping is in order before we get started. Today's program is registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. AAA members, please provide your member number to your local host before leaving today's session. Credit for attending this program can also be applied toward the LEED Credential Maintenance Program or your Professional Engineer's License. So PEs, please check your state's requirements. Variable speed drives are available on chillers with compressors of all types. Today, we'll discuss the operational, performance, and application differences for centrifugal, dynamic compression, and helical rotary or screw compressors. We'll start with a brief overview of how variable speed drives affect chilled water system components, then get into the physics of centrifugal compressor chillers and screw compressor chillers. We'll highlight some applications that benefit from each technology, then discuss the importance of life cycle analysis, and finally, we'll wrap it up with some application considerations. To cover the information today, we have a guest from our Pueblo plant, Mike Filler, who is the product manager for Trane water-cooled screw and scroll chillers. We'd also like to introduce a new face from our team, Brian Sullivan, one of our Trane systems engineers. And you're most likely familiar with Lee Klein, systems engineer, and Mick Schwedler, application engineering manager. Mick will get us started by laying the groundwork for today's discussion. Mick, take it away.
Thanks, Jeannie. Let's take a few minutes to frame the discussion on how variable speed drives affect different system components. Then Brian and Mike will discuss how centrifugal and helical rotary or screw chiller performance changes when variable speed drives are applied to them. Many of us are familiar with the affinity laws, often referred to as the fan laws or pump laws. In the 2012 ASHRAE Handbook chapter on centrifugal pumps, the three affinity laws can be summarized. Flow is proportional to speed, pressure is proportional to the square of the speed, and power is proportional to the cube of the speed. Now, one assumption from the handbook that is often overlooked is that the device, in this case a pump, is acting in a system where the head or pressure difference varies as the square of the flow. As we're going to see shortly, the pressure difference for various chilled water system components does not always vary with the square of the flow rate. While we'll be concentrating on the chiller today, we'll touch briefly on the chilled water pumps, the condenser water pumps, and the cooling tower fans. Let's move through the components from those that come close to achieving the promised affinity law performance to those that are furthest from achieving the near cubic savings. Let's first examine cooling towers, which are free discharge devices. The air path resistance is almost totally due to frictional losses, since there's nothing but friction to influence the airflow resistance. Even so, the power draw of a cooling tower fan does not exactly decrease to the cube of the tower load. The bottom line on the chart represents the fan power decreasing to the cube of the fan speed. The top line represents an example of a cooling tower's actual performance if controlled to an 85-degree set point, which would reduce the fan speed as quickly as possible. As you can see, it's close to the ideal performance, but not quite that good. This is because there are other influences on the tower performance, such as water and airflow patterns and evaporation rates. Even so, a cooling tower is the component of chilled water system which operates closest to ideal of the cube of the speed power reduction with the load. Next, chilled and condenser water pumping systems both have a fixed or controlled pressure component and have minimum flow requirements. These prevent the pump energy from following the ideal curve. Specifically, in many variable flow chilled water systems, there is a system differential pressure set point the pumps must meet. For condenser water systems, the lift from the tower sump to the distribution nozzles is a fixed value. This chart shown here provides an indication of how these fixed pressures keep the pressure drop from changing with the square of the flow rate. In addition to this pressure not following the square relationship, there are minimum flow requirements. During normal operation, the condenser water side flow rate must be maintained above the higher of the chiller condenser minimum and the cooling tower minimum. On a chilled water system, the flow rate must be above the evaporator's minimum flow rate requirement. So not only is the power curve not cubic, but it actually becomes nearly constant power once that minimum flow rate is reached. Now, on chillers, variable speed drives react differently than on tower fans or pumps. That is not because the affinity laws change. Rather, it is that in most cases, the assumption that the head or pressure drop varies with the square of the flow is not true. For a chiller, the head is dependent on external parameters. The pressure drop the chiller's compressor must overcome is proportional to the difference between leaving condenser water temperature and the leaving evaporator water temperature. If the compressor lift changed with the square of the refrigerant flow rate, the power would change with the cube of the flow rate. However, in most cases, the lift does not change with the square of the flow rate. Next, the work the chiller performs is based on the load or capacity and the lift. Finally, centrifugal compressors are aerodynamic devices, while rotary screw compressors are positive displacement devices. Their characteristics differ. You'll also see that at the various operating conditions, the compressor efficiency changes, which directly affects chiller performance. To help us understand those differences, we brought in Brian and Mike. As you'll soon see, they have a wealth of knowledge specific to how compressors, and therefore chillers, react when their speeds are varied. Hang on to your hats as you learn from them. Then Lee and I will be back to talk about applications of variable speed drives on chillers and changes to our system design and operating paradigms if they are used. Brian?
Thanks, Mick. To begin, let's list 4 points that we will be discussing in detail. 1, to develop mathematical relationships for chiller energy use, we need to develop an idea of how work varies with different operating conditions. This first point addresses the amount of work a chiller needs to do and how the lift across the chiller is just as important as the chiller tons. 2, modern fixed-speed centrifugal and screw chillers have mechanical capacity modulation devices. How good are they? 3rd, variable speed is another form of modulation. How does this option fit in, and what performance advantage does it have? And lastly, given that we can obtain both fixed-speed and variable speed chillers, how might one decide which is best? Regarding the first point, we need to develop a unit performance equation. In common practice, kW per ton is generally referred to as unit efficiency. However, for the purposes of this discussion, we need to use the term efficiency in a more traditional way, where efficiency is used to compare the ideal amount of power to the actual power used for a given quantity of work. Please note, this efficiency term includes all efficiency components, including motor and compression efficiency, as well as the efficiency related to refrigerant and refrigeration cycle. The first thing we need to determine, given this definition of efficiency, is the ideal power requirement. The Carnot relationship for a refrigeration cycle is used to give us a measure of the amount of power needed for the ideal performance cycle. A quick search on the internet will remind us that the Carnot coefficient performance, or COP, is a function of the cold and hot temperatures. Rearranging the equation and applying unit conversions, we find that an ideal kW per ton performance is proportional to the lift in temperature divided by the cold temperature value. If we assume that the cold temperature remains constant, then we find that the ideal power is proportional to the capacity in tons multiplied by the temperature lift. Letting lift be equal to the difference of the leaving condenser water temperature and the leaving evaporator water temperature, we find the actual power input is proportional to the capacity in tons multiplied by the lift and divided by the unit efficiency. Now let's take a look at how this relationship can be used to predict unit performance. If we assume that the unit efficiency achieved at full load is the same as the unit efficiency at part load, we can scale the full load kW per ton performance by any change in lift to predict a unit performance target at part load. For a given chiller, this is an aggressive part load target. So let's see what the unit performance target looks like for a constant entering condenser water temperature of 85 degrees. Looking at this graphic, we can see that even though the inlet condenser water temperature is constant, the leaving condenser water temperature is reduced as the chiller load is reduced given a constant condenser water flow rate. Therefore, the lift term goes down slightly as the operating load or tons goes down. Because of the reduced lift, the kW per ton target performance improves. So if the preceding kW per ton performance trend is likely the best we can expect from a modulation system, what's the worst? For this case, let's examine a compression device that does not modulate, but instead uses capacity control external to the compressor. The most common form of this is hot gas bypass. It regulates the compressor capacity by selectively bypassing compressed gas back to the suction. Only that amount of refrigerant vapor needed to meet the cooling load condenses and then expands into the evaporator to complete the cycle. The compressor flow rate and power remain nearly constant during operation. For hot gas bypass, all the power needed to compress the bypass gas is discarded, doing no beneficial work. Looking at unit performance, or kW per ton, in conjunction with the hot gas bypass cycle, this slide illustrates how inefficient this modulation system becomes at part load. As the amount of bypass gas increases, the capacity or tons of cooling goes down. With the compressor flow and work remaining nearly constant, the input power per unit of refrigeration capacity, or kW per ton, goes up dramatically. ASHRAE 90.1 caps the amount of hot gas bypass to 10% of the compressor capacity. In practice, it is a good idea to avoid the use of hot gas bypass entirely unless dictated by a need for extremely low unit capacity modulation. Now that we have bracketed very good and very bad part load performance on the kW per ton chart, let's examine the inlet guide vane modulation method employed on centrifugal compressors. Centrifugal compressors use inlet guide vanes to redirect and modulate the refrigerant gas flow internal to the compressor to achieve a much more efficient operation when compared to hot gas bypass. With inlet guide vane control, the performance curve for an 85-degree entering condenser water temperature is shown on this slide. For inlet guide vane modulation, the performance is quite good at high load points in that the performance stays close to the ideal target performance line. Now let's expand the operating map to consider entering condenser water temperatures that are less than design. For this chart, we've dropped the hot gas bypass curve so the y-axis scale can be expanded. The 85-degree entering condenser water temperature curves are displayed. The actual performance displayed as the solid line, the ideal performance target with constant unit efficiency is displayed as the dashed line. Let's first expand the operating map by displaying performance targets for more part lift conditions. Similar to the 85-degree line, this next line represents the target performance at 75 degrees, 65 degrees, and finally the 55-degree line. The performance improvement has the potential to be quite good due to the reduced work at low lift conditions. In comparison to these more ideal part lift target curves, the actual chiller performance at these same entering condenser water temperatures are 75 degrees, 65 degrees, and 55 degrees. Note that fixed speed centrifugal chillers perform very well when the load and lift is near design. Also, the performance in terms of kW per ton does improve with reduced tower water temperature. However, it increasingly falls short of the more ideal target performance values as the lift is reduced. Now that we have an overall view of the performance for fixed speed chillers, let's look at how the compressor operates. In this slide, we look at a more traditional compressor operating map where the pressure rise of the compressor is illustrated on the y-axis and the flow rate of the compressor is shown on the x-axis. The flow rate of the compressor is proportional to the capacity of the chiller, or tons. Let's first examine the extremes of the compressor operating envelope. The maximum capacity of the unit is shown at the wide open inlet guide vane curve. For an aerodynamic device such as this, the design speed and the compressor impeller diameter dictate the maximum flow rate and pressure rise. As with other aerodynamic devices, such as pumps or fans, the compressor will ride this curve to achieve a flow rate at the required lift for a given operating point. If the chiller conditions call for a pressure rise that cannot be achieved at the uppermost position of the vane curve, the compressor will surge. To actively modulate the compressor capacity, the inlet guide vanes close to redirect and restrict the refrigerant flow through the compressor. In operation, the compressor can be run at any guide vane position between a minimum and maximum value. Now, viewing the compressor operation boundary, the minimum and maximum guide vane positions detail the minimum and maximum cooling capacity limits, and the surge boundary defines the uppermost lift capability. Adding compressor efficiency contour lines to the operating map, we find the peak efficiency generally occurs near the selection design condition, with decreasing efficiency as the load and the lift decreases. Continuing on, let's put the compressor operating map side by side with the chiller performance chart, and then look at the 85-degree entering condenser water condition. In this case, the 85-degree unloading line will intersect the surge boundary at about a 25% load point. Note that it is important to ensure that centrifugal compressors can unload to a low operating point at this design entering condenser water temperature to ensure the unit does not surge in the event of a system issue. Since the surge boundary is established at full speed operation, the surge point is important whether the unit operates as a fixed speed or variable speed chiller. As a result, many engineers specify this unloading requirement on behalf of their customers. Because of our multi-stage compressor design and selection rules that verify the chiller will operate down to a 25% load point at a design entering condenser water temperature, we rarely use hot gas bypass to extend the operating map. Continuing on with the comparison, you see how compressor operation at lower condenser water temperatures operate at lower compression efficiencies. However, even though the compressor efficiency is reduced at lower pressure rise values, the reduced work at the lower condenser water temperatures results in improved chiller kW per ton values.
We've covered quite a bit. Let's review and summarize the first two key points. 1, ideal kW per ton performance is a function of the temperature lift across the chiller. As discussed, we use a Carnot relationship to define the ideal work associated with the refrigeration cycle. This in turn provides target performance trends for the chiller at various lift conditions. The amount of work that the chiller accomplishes is just as dependent on lift as it is on tons. And 2, that fixed speed centrifugal and screw chillers with mechanical unloading devices effectively reduce tonnage and take advantage of reduced lift. Brian explained centrifugal chiller operation and showed that even though compressor efficiency declined, the reduced work associated with lower lift conditions results in improved kW per ton performance. A bit later, we'll examine screw compressor performance. But now, let's have Brian help us understand variable speed centrifugal chiller operation.
Although variable speed compressor operation has been around for some time, the very early systems were generally restricted to more exotic methods such as turbine drives or engine-driven chillers. Variable speed compressors have become more mainstream based on the reduced cost and improved reliability of the variable frequency drives. However, this tends to be more applicable to drives with input voltage less than 600 volts. Drives above 600 volts continue to be quite expensive, typically doubling the first cost of the chiller. For variable speed performance, we will view charts that have the same arrangement of terms we used earlier for the fixed speed compressor. We start by looking at chiller kW per ton performance trends compared to the ideal part load performance targets. Shown here is the 85-degree condenser water temperature load curve. It doesn't look much different than that of the fixed speed chiller, since full or nearly full speed is required to achieve this load curve without surging. Additional performance curves are shown for the 75-degree entering condenser water temperature, the 65-degree, and finally the 55-degree curves. Note the kW per ton performance for variable speed compressor approaches the part load ideal efficiency targets. For the centrifugal chiller, this peak compression efficiency is achieved at a combination of both lift and load reduction. Shifting to an operating map for a variable speed compressor, we note the full speed operating limits look just like the fixed speed map shown earlier. Both the maximum capacity and surge boundaries are identical. If we next examine how variable speed modulation modifies the compressor operating map, we see that the entire map scales to the operating speed. Similar to variable speed centrifugal pumps and fans, the capacity scales linearly with speed, whereas the pressure rise scales to the square of the speed. From a performance perspective, we see the best efficiency zone associated with operation near the design point is swept through the operating map when the speed is optimized for a given operating point. This is the essence of the affinity laws mentioned earlier. However, the compressor speed can only be reduced if both the load and lift requirements fall together. This is not a given for centrifugal chiller operation. To provide operation over the full operating map, the compressor speed must be controlled to meet the worst case of the chiller lift or load imposed on it. The result is that when a variable speed drive is applied, some combination of speed and inlet guide vane control is needed to both optimize for energy use and provide reliable operation over the entire map. Contrary to popular belief, there is no centrifugal chiller in production that does not include both modulation methods. Looking at different portions of the operating map, the compressor capacity modulation relies on different control algorithms. In the high capacity region of the operating map, speed modulation is generally all that is needed to modulate the compressor flow. In this region, the system will ride the wide open guide vane curve to achieve the balance point between the needed pressure rise and compressor flow rate. For operating points near full lift conditions, the compressor must operate near full speed in order to create the needed pressure rise. In this region, the capacity modulation relies most heavily on guide vane control. And finally, at a combination of lower capacity and lower lift, the speed and guide vane control must be highly coordinated to optimize the speed for the pressure rise required, but also to further regulate the compressor flow rate with guide vane control. Putting the kW per ton performance chart side by side with the compressor map, we can now gain some insight as to how the best chiller performance coincides with operation detailed on the compressor map. Operation at the 85-degree entering condenser water temperature is not much different as compared to fixed speed operation. The performance is similar, and the same considerations regarding surge come into play. However, as one might expect, as the load and lift is reduced, the improved compressor efficiency associated with variable speed operation results in performance that approaches the ideal part load performance targets. Now that we have looked at both the fixed speed and the variable speed compressor maps and the performance curves, let's do a comparison of the two. The comparison is based on equal priced chillers. To start, a variable speed chiller was selected at near ASHRAE 90.1 minimum efficiency levels to establish the chiller cost. The same cost was used to select the fixed speed chiller at the same conditions. The centrifugal chillers were selected at 900 tons, but the comparison is fairly representative across the product line. This slide provides the performance details of the two same price chillers. Looking at the chart, the variable speed performance is shown as the dashed lines, and the fixed speed performance is shown as the solid lines. The fixed speed machine at 0.513 kW per ton had a much better design point efficiency as compared to the variable speed selection at 0.585 kW per ton. This difference at design conditions results in about 12.5% efficiency advantage for the fixed speed chiller. Approximately 3% of the improvement is associated with drive losses, with the remaining 10% coming from improved heat exchangers for both the condenser and the evaporator. A couple of things to point out. For the 85-degree curves, the fixed speed chiller always has a lower kW per ton value. At the other extreme, for a 55-degree entering condenser temperature, the variable speed kW per ton is almost always better. For the temperatures in between, the comparison is a bit more involved. So let's take the data and revise the way we look at it. The comparison will be much clearer. For this chart, the y-axis is changed to the leaving condenser water temperature. By looking at the leaving water temperature, we can more clearly see the impact of lift reduction needed for the performance improvement of the variable speed compressor. As in previous charts, the chiller load is shown as a percent of full load operation on the x-axis. To generate the lines on the chart, the previous kW per ton performance data was compared, a percentage improvement computed, and contour lines drawn. The 0% contour line illustrates those operating points where the kW input is the same for either the fixed or the variable speed chillers. Above and to the right of the 0% contour, the fixed speed chiller has better performance. Below and to the left, the variable speed chiller performs better. As one readily notices, the variable speed part lift improvement can be quite a bit better than that of the fixed speed chiller. However, the tower control system must be run at lower condenser water temperatures to provide the improvement. As informative as the contour chart is, it's still not obvious whether a fixed speed or variable speed chiller is best for a given application. And that's the key. We need to look at the application of the chillers within the chiller plant to determine how they might best be applied. But before we get to that, we need to catch up on how the rotary screw chillers perform. Mike will be going over that information.
Thanks, Brian. There are more than just centrifugal style compressors to use on chillers. In switching over to positive displacement compressors, it's a good time to point out some of the differences, or at least generalizations. There are 3 positive displacement compressor styles in use for water chillers. Scroll and rotary screw compressors require less maintenance and tend to have higher reliability, due in part to having much fewer moving parts. Reciprocating compressors are still used in certain niche applications, but most smaller HVAC compressors are scroll style now, with up to 30 to 40 tons per compressor. When it comes to HVAC applications, rotary screw compressors fit nicely in between scroll compressors and centrifugal compressors. For roughly 30 years now, rotary screw chillers have been offered in overlapping capacities as small centrifugal chillers, from around 35 tons to upwards of 450 tons or more. For the purposes of these discussions, we're going to focus on rotary screw compressors. But before we get into the details of rotary screw compressors, let's take a closer look at one of the big differences in how the centrifugal compressor operates versus a rotary screw compressor. For a centrifugal compressor, without taking mechanical unloading into account, the flow, and in turn the capacity, would ride the curve as pressure differential, or chiller lift, conditions change. Again, this is without any unloading built in, which is nearly universal for centrifugal chiller applications. For a given rotary screw compressor, the volumetric capacity is not significantly affected by lift. It's a nearly vertical line. This is not to say that capacity, or more importantly, the efficiency of rotary screw compressors won't change with varying conditions. The point is that lift reduction has very different effects on the chiller, depending on the style of compressor being operated. Many people may not be familiar with how a helical rotary screw compressor works. Viewing the compressor from the top shows that after the pockets of refrigerant travel through the intake area, the vapor is confined within pockets created by two helical rotors, one of which is driven by the motor. The continued rotation of the meshed rotor lobes causes the meshing point to travel through the discharge end of the compressor, driving the trapped refrigerant vapor ahead of it. This action progressively reduces the volume of pockets compressing the refrigerant. The compressed gas is then pushed out the discharge ports. Rotary screw compressors can be unloaded mechanically through the use of ports or slide valves. With a port or plug valve, some portion of the compression volume is allowed to recirculate back to the suction in stepped capacity increments. The use of a slide valve is now the most common method for unloading rotary screw compressors, and it tends to add tighter accuracy to the chiller's temperature control. At full load, the slide valve is closed. The compressor pumps its maximum volume of refrigerant, discharging it through both the radial and axial ports. At part load, the slide valve modulates toward the open position. The opening created by the valve movement allows the refrigerant vapor to bypass from the rotor pockets back to the suction side of the compressor. This reduces the volume of vapor available for the compression process. It also reduces the amount of rotor length available for compression. In this manner, the volume of refrigerant that is pumped by the compressor is varied, unloading it to meet the existing chiller load. This slide is similar to what Brian shared on centrifugal chillers at fixed speed. Here is a kW per ton relationship over a range of capacities with a constant 85 degree Fahrenheit entering condenser water temperature. The ideal target performance line at a constant compression efficiency is shown and compared to unloading with a slide valve and unloading with hot gas bypass. Hot gas bypass has become much less common. It is also limited by energy efficiency standards such as ASHRAE 90.1 starting in 1999. The slide valve performance is quite good at high load points in that the performance stays close to the ideal target performance line. This is another slide similar to centrifugal chillers with fixed speed unloading. The dotted efficiency lines represent the ideal target performance at a constant efficiency with various lift conditions, entering condenser water temperatures from 55 to 85 degrees Fahrenheit. And now, the solid lines are the efficiencies of a rotary screw chiller with slide valve unloading at the same varying entering condenser water temperatures. Similar to centrifugal chillers, at lower capacities, screw chiller efficiency with slide valve unloading tends to drift away from the ideal target performance. Now that variable speed drive costs continue to come down, it has become more common to see them on the likes of rotary chillers. Some rotary screw compressor manufacturers apply variable speed drives in conjunction with a slide valve, port, or added mechanical unloading capability. Other designs apply the variable speed as the only means of unloading. One last time here, I'll display the ideal target performance as dotted lines representing various lift conditions, entering condenser water temperatures from 55 to 85 degrees Fahrenheit. And now the solid lines represent a rotary screw chiller unloaded with variable speed at the same varying entering condenser water temperatures. This now begs a comparison between fixed speed and variable speed. When comparing the performance of a chiller model available with and without variable speed, a consideration has to be made to the added cost of the variable speed drive. If you compare the same unit with and without the variable speed, there would be a 2 to 5% hit at full load efficiency that is quickly overcome in part load operation. This graph compares a fixed speed chiller that has improved heat exchangers to illustrate the difference between units that would roughly cost the same. Adding a drive to the unit with improved heat exchangers would certainly improve performance, but a life cycle cost analysis would be needed to confirm the payback for the higher initial chiller cost. Here's an illustration of the difference in performance for equivalently priced units, one with fixed speed slide valve unloading versus variable speed unloading. Lift is represented on the y-axis in terms of leaving condenser water temperature, while chiller load is shown as a percent of full load operation on the x-axis. The area to the left of the break-even or 0% curve indicates conditions of reduced power use for the variable speed chiller. If a majority of the operating hours occur with 75 to 80% load or less, then a variable speed drive makes sense on a rotary chiller, with or without lift reduction.
Mike, given what you and Brian have discussed, people are probably wondering how centrifugal and rotary chillers with drives compare.
The quick takeaway, if they both have variable speed drives, is that rotary chillers don't lose as much efficiency at low loads, especially with high condenser temperatures. The simplistic reason for this, as Brian had shared, is that centrifugal compressors need reduced capacity and lift reduction to take advantage of lower speeds. This is not true for positive displacement compressors. In other words, rotary compressor speed modulation is primarily a function of capacity, but centrifugal compressor speed modulation is a function of capacity and lift.
With that said, the screw and centrifugal chiller design efficiency might be different. Since that's the starting point for any analysis, generalizations are hard to make.
True. How about if I summarize what we've gone through? Since rotary compressor speed reduction is a function of capacity, variable speed rotary chillers can make sense in hot and humid climates, even on applications where all variable speed drives in a plant with centrifugal chillers would not have been justified, since there may not be many hours with lift reduction in hot and humid climates. Most rotary chillers on the market are available with fewer configurable choices compared to centrifugal chillers. That means there are commonly gaps in capacity for the available rotary chillers. In the past, that generally indicated worse full load efficiency when a rotary chiller with mechanical unloading was used at less than its maximum capacity. However, since the unloading with variable speed improves efficiency, even at constant lift, it may make sense to use a slightly oversized rotary screw compressor with a drive. There is a limit to oversizing, since many chillers often end up operating at or near minimum load. The variable speed drive offers an added opportunity to optimize the capacity and efficiency of rotary screw chillers. Today, our rotary chillers have better acoustic performance than older generations. Full load sound levels are around 7 to 10 decibels lower than rotary chillers that are less than 10 years old. Meanwhile, some competitor centrifugal chillers in the last 10 years have substantially increased their full load sound levels, due in part to much higher speeds at full lift or full load. If low or specific sound levels are needed, specify the performance at full load or worst case. Both centrifugal and rotary chiller manufacturers have been improving reliability and efficiency over the years. In general, the best full load efficiency practically available for a centrifugal chiller is better than for a rotary chiller. With that said, some rotary chillers are capable of meeting the energy code efficiency requirements for centrifugal chillers. When that occurs, it's best to write a specification that allows either compressor technology and use a life cycle cost analysis to compare chiller performance and other associated long-term costs. In short, select the better performer regardless of technology. And a final difference to remember is the capacity limitation for rotary screw compressors. Manufacturers for rotary screw compressors in HVAC applications tend to be limited to the 450-ton range, while centrifugal chillers are available up to thousands of tons.
Mike and Brian, thanks for those explanations. The first aha I take away from these discussions is that, as should be expected, the physics of operation of a centrifugal or dynamic compressor and a positive displacement compressor are quite different. And while it's very interesting to me to understand these fundamentals, the more important thing to remember is that their part load performance varies depending on the capacity modulation method used and the application operating conditions. However, for a given modulation technique, whether wasteful hot gas bypass, good mechanical modulation, or variable speed modulation, when you do an apples-to-apples comparison of any one modulation method on different compressors, the chiller's performance will look pretty similar for typical HVAC system operating conditions. The second important thing to remember is the reason the chillers perform similarly is that regardless of the compressor or chiller type, the major determining factor of chiller energy consumption is the work that is imposed on the chiller by the system. On a theoretical level, load and lift have independent and equal impact on the work the chiller must perform. On a practical level, it's not quite that simple. System and unit operating limits and multiple changing efficiency terms result in a bit more complex relationship between the two. But generally, the result of this is that the best performance is achieved when the refrigeration load and lift rise and fall at a similar rate. A third observation from Brian and Mike's discussion is relative to the difference in the selection and design process for centrifugal and screw chillers. Centrifugal compressors are typically selected and manufactured for a job-specific design conditions. Screw compressors are manufactured in capacity and lift families, and the compressor that most closely matches the job requirements is applied to its chiller. Because of a screw compressor's inherently broad operating map, the same compressor can be applied with confidence on a wide range of applications. What this means from an energy point of view is that centrifugal chillers have more opportunity for application and efficiency optimization for any given job's part load and full load conditions. In any case, for the vast majority of applications, manufacturers can provide either a centrifugal or a screw compressor chiller that will perform reliably, stably, and efficiently for many years of operation. The last observation to make relative to chiller performance is that there is very little difference in the operating limits of the chillers for a certain design of constant speed compressor compared to the same compressor in a variable speed configuration. This makes sense from a high lift, high load point of view because the controls can speed up the compressor to meet the required lift and load up to what would be the fixed speed compressor's design speed. From a part load, low lift point of view, the variable speed modulation method can slow the compressor to a similar minimum load point as traditional compressor modulation techniques, such as inlet guide vanes or a slide valve. And in many refrigeration systems, the minimum load point is not actually set by the compressor, but by other system requirements, such as an expansion valve control limit, minimum differential pressure, or oil flow requirements. As discussed, the biggest performance difference between centrifugal and positive displacement compressor technologies is that in the applications with constant, elevated condenser water temperatures, a screw chiller can unload with no chance of compressor surge. That doesn't mean a screw compressor can operate with any condensing conditions. Higher than designed condensing conditions can result in bearing loads or discharge refrigerant temperatures that can damage the compressor. But under normal operation, it does avoid the surge concern. The surge resistance of a centrifugal compressor varies greatly depending on the compressor design and selection. Low pressure, multi-stage compressors typically unload to 10 to 15% load with constant entering condenser water temperatures without risk of surge. However, many of the high-speed single-stage centrifugal compressors cannot unload nearly that far without the benefit of significant lift relief or the application of energy-wasting hot gas bypass, something you may see marketed under the term range extension system by some manufacturers. With all this talk about part load performance, we dare not neglect to mention the importance of full load chiller performance to system efficiency and improving financial ROI. For any given modulation technique, the chiller's full load efficiency anchors its ultimate part load efficiency. Putting a variable speed drive on a chiller is an upfront investment which may have a relatively long financial return on investment depending on the specific application. This begs the question, how can the return on investment be maximized and the payback period be minimized? Mick and Brian will discuss this more in a moment, but an interesting result of an analysis that includes real utility consumption and demand charges reveals that the plant efficiency, and importantly for this discussion, the plant financial ROI can be significantly improved by investing in a variable speed chiller that includes premium full load efficiency. In this case, double dipping by specifying variable speed control to reduce electrical consumption costs and premium full load efficiency to minimize demand as well as consumption cost is typically the best financial investment. Mick, I think it's time to switch to some application considerations to help us understand where variable speed compressor technology brings the most benefit.
Thanks, Lee. So how can we benefit from the information just shared with us? For centrifugal chillers, seek conditions at which the chillers will operate with reduced lift. In addition, it will be even more beneficial if the variable speed chiller will be loaded below 80%. For screw chillers, look for applications when either load or lift are reduced. And if they're both reduced, it's even more beneficial. Now, does that mean that every screw chiller is a candidate for a VSD? That depends on the economics. So we'll also look at some evaluation tools. Now, let's look at some applications that have recently come across our desks. The goal is to determine if further financial analysis regarding the purchase of a variable speed chiller is warranted. Our first example is a data center expected to operate with chillers nearly full load once it's built out. In this case, we'll put it in Kansas City, and they've decided not to include air side economizers. In this case, there will be a lot of operating hours at reduced lift because there will be many hours below the design wet bulb temperature. In addition, if the redundant chiller is used during operation, the load per chiller would be below 80% and save even more energy. So this would be a good candidate for an analysis to determine if the return on investment justifies purchase of 1, 2, or 3 variable speed drives. Now, let's locate that data center in a cold climate instead. In this case, the data center was also designed at a higher leaving water temperature, 75 degrees, and it has an air side economizer. There will be few hours of operation at either reduced lift or load. In fact, the chiller will be off during a lot of hours. so it's unlikely a variable speed drive will pay back. The second example happens to be a hotel in Caracas, Venezuela, but it could be any job in a hot and humid climate that operates for a lot of hours. In a hotel, there are a lot of hours at reduced loads, specifically at night or times of low occupancy. But since it's always humid in this climate, there are few hours of reduced lift. Variable speed drives on centrifugal chillers are not going to save much energy at all. However, we might decide that a small swing chiller that will operate at low loads may be a very good candidate for a screw chiller with a variable speed drive. So an economic analysis is warranted to see if the investment is justified. Now later, Lee is going to discuss the use of swing chillers, and we'll see if variable speed drive chiller performance might change our paradigms. The final scenario we'll examine is a retrofit that achieves additional building capacity by adding ice storage to an existing system. Now note that the ice storage system is isolated from the building by using a heat exchanger. The chiller makes ice at night to charge the tanks, and during the daytime, the chillers operate to augment the ice tanks. So when it's hot and humid, but during the day, the chiller produces warmer fluid. So even though the cooling tower water temperature will likely be higher than at night, the lift is reduced. On non-design days, the lift can be reduced significantly. In addition, when the chiller is running during the day, there are a number of hours that the chiller operates at reduced load. So this looks like a real good opportunity for variable speed drives to be analyzed. Now let's take the same system, but change the mode of operation to full ice storage. That is, the chillers only operate at night, and when charging the tanks, chillers are operated at full load. In this case, there is no load reduction experienced. But lift may be reduced in temperate climates for the many hours when the outdoor air conditions are less than design. So this is less likely to pay back than the previous ice system, but probably still warrants analysis. So when an analysis is warranted, what tools are available that don't take a lot of time but can get you in the ballpark? Now, I often turn to Chiller Plant Analyzer, which is a subset of Trace that takes away all that time-consuming part of Trace. And if you have Trace, you already have Chiller Plant Analyzer. By inputting your location, the building type, and whether there is an economizer, then describing the base chilled water system type and the building design load, a load profile is generated. This allows analysis of chilled water system type, chiller sizes, utility rates, thermal storage, etc. And for our purposes, chillers with and without variable speed drives. This can be completed literally in 30 to 40 minutes, and you'll have information to share with your clients. Now, there are two analysis mistakes that I see made quite frequently. Let's address those to make sure you get the right information to share with your customers. Remember that Brian told us that chiller performance is a result of the load and the lift. When you request chiller performance from manufacturers, including us, it's likely that you'll get data like that shown on the screen. Notice that this data couples load and lift. For example, at 50% load, the lift is assumed to be reduced by 20 degrees, from 85 to 65. But the fact is that any load condition can occur at any lift condition. And there are various ways to model all these operating points. But why does this matter? Well, let's take the case of a humid climate. The chiller may operate at many different load points, but not reduced entering condenser water temperatures. So performance data would be closer to that shown on the right. For example, at the 50% load point and 85-degree tower entering temperature, the kW is 80% higher than if we incorrectly use that data in the left chart. That's a big miss. So how is this information properly incorporated into modeling tools to produce accurate results? A common method used in Trace and Chiller Plant Analyzer uses two curves, an unloading curve and a lift or ambient relief curve. What happens if we input the data that includes both load and reduced entering condenser water temperature without thinking through the process? The curve shown on this screen results. However, after the program performs this power and load calculation, this outcome is multiplied by the second curve. The final calculation will double account for the lift reductions. So how bad is that? Let's look at two examples. If the system is in a humid climate where the tower temperature is constant, the chiller will actually perform along the curve shown. But if the data is input improperly, the analysis will double account for lift reductions. With this incorrect input, the performance within the program will be the bottom curve. That's a significant energy reduction, about 30 to 40%, that is not going to be realized by the building owner, and they are not going to be happy. Now, what if we move the system to a more temperate climate, where lift reduction can occur at reduced loads? The actual energy use would fall along the top line, but the calculated energy use would be the bottom line. Again, energy savings is significantly overestimated. In either climate, by inputting the data incorrectly, the simulated performance is much better than actual, which, by the way, makes a variable speed drive look really, really good no matter what, but disappoints the building owner. So make sure to input the data correctly into the modeling tool. The second concept is making sure the economic comparison is done properly. Brian and Mike compared two same price chillers, one with a variable speed drive, the other premium efficiency with more heat exchange surface. This makes sense because building owners are interested in their return on investment, and whichever saves more helps them reduce their costs. Recall that the premium efficiency chiller has 12.5% lower power than the variable speed drive chiller. A problem occurs if the demand and consumption charges are lumped into a combined utility rate. When this is done, the estimated utility cost of the variable speed drive chiller will be significantly lower than the actual operating cost. That's because the 12.5% additional demand charge is not accounted for. So use the actual utility rates and keep demand and consumption charges separate. Okay, the last subject I'll cover is a new analysis tool that's even simpler and quicker than Chiller Plant Analyzer. It's called MyPLV. The goal is to give you a quick tool that is based on a profile and climate that is custom for you. Using MyPLV, you select the type of chiller, air-cooled or water-cooled, the location, and the building type. These choices are used to retrieve a load profile that was developed by Pacific Northwest National Labs for use by the ASHRAE 90.1 committee. Then you input the design load, number of chillers, and chiller capacity. Using this information, a weighted and personalized chiller profile is output for your project, and that load profile is based on data from a national laboratory. You then define your consumption and demand rates, including a ratchet charge if applicable. Following that, you get performance ratings for the chillers that you're considering, and you can quickly compare options. And remember, the performance is at your project's custom-weighted conditions. So let's look at a few examples for screw chillers and use MyPLV to perform a quick chiller analysis in each case. We're going to have two chillers sized to meet the 530-ton load, with consumption costs of 6 cents a kilowatt hour and $12 per kW demand charge. The base system chillers meet 90.1 2010 requirements. The first alternative is a variable speed drive chiller. This chiller is allowed by 90.1 to have a higher full load kW per ton due to the inefficiency of the drive. The second alternative is a premium efficiency chiller that has about the same price as the variable speed drive chiller. Instead of investing in a variable speed drive, the money is put into more and better heat exchange surface, copper, to arrive at the higher efficiency. The additional price is as close as possible to that of the variable speed drive chiller. The third alternative is to select a premium efficiency chiller with a variable speed drive. Now, using these parameters, let's start with an office building in Houston. This system has an air side economizer per 90.1 2010. We first get the chiller performance values at the various load and entering condenser water conditions. These come from the manufacturer's selection program. We then input that information into the light blue cells. Calculations are performed below, and we see that while either the VFD or premium efficiency option has a good payback, the premium efficiency chiller gives superior payback. This is primarily due to the demand charges assumed. Finally, with more heat exchange surface and a variable speed drive, we see a payback of 2.6 years, which would be acceptable to a lot of building owners. Next, we'll move to an existing hospital in Lexington, Kentucky. And in this case, the hospital does not have an air side economizer. Even though the demand charge is higher, the variable speed drive chillers have a quicker payback than a constant speed premium efficiency chiller. But if an AFD is added to that premium efficiency chiller, the payback is the same as just an AFD, and there are additional energy and energy cost savings available. We could keep doing analyses for a long time, but the fact is, none of them would be your project. MyPLV and Chiller Plant Analyzer were developed to allow you to do those analyses quickly and for your custom conditions. Now, Brian has used the MyPLV data to perform some further analysis on centrifugal chillers. Let's bring him back to share that information.
Thanks, Mick. In the last couple of slides, Mick introduced the MyPLV tool. In these next slides, I'm going to use MyPLV and the simulation data to go into more detail to compare variable and fixed speed centrifugal chillers. Let's consider this first application, a large office building located in Houston, Texas with an economizer, a peak load of 1,600 tons with 2 centrifugal chillers. The cooling tower runs an optimization algorithm with the result being a leaving tower water temperature that varies with outdoor wet bulb. This standard chart from MyPLV details the hourly operating points for the chilled water plant. The chiller plant loading and entering condenser water temperature are as shown. Each blue data point on the left side of the data map represents an hourly condition where a single chiller is sufficient to meet the plant load. The smaller grouping of red data points to the right start above 900 tons and represent those operating conditions where both chillers are needed to run. Note that only the first chiller will see the full range of conditions from low to high capacity and low to high lift and is responsible for 76% of the total plant ton hours. The table at the bottom of the slide is a standard MyPLV output that provides the weighted load points for the total chiller plant and the weighted load points for the individual chillers. All of these weighted load profiles will be examined in more detail in the next few slides. But before we use the weighted load profiles, let's first take a look at the scatter plot for the individual chillers and compare them to the earlier contour plot that was developed for equally priced centrifugal chillers. This chart we've seen before. While it's not part of MyPLV, we can overlay the chiller operating points onto this contour chart developed earlier for the equally priced chiller comparison. Remember, the area below the 0% line benefits the variable speed chiller. Above and to the right, the fixed speed chiller performs better. Also, the percent savings can be a little misleading. For example, it would take 3 hours of operation at 30% load and a 75-degree leaving condenser water temperature to offset 1 hour of energy use at 90% load and 90-degree leaving water temperature. So as the load reduces, you need more hours of operation, or DOTs, to offset additional energy use. Okay, so let's look at the operating profiles for the two chillers. The first chiller operates quite a few hours at conditions where variable speed drive saves energy, and a decent number where it uses more energy. Even so, at first glance, it looks to be a good candidate for a variable speed drive. How about the second chiller? Whoa, this chiller only operates at relatively high load and at high temperatures. Almost all the operating hours for this chiller are in the regime where a same price fixed speed chiller is a better choice. Although these charts provide a good visual of how the two chillers in this plant run, we really need some hard numbers to better determine which chiller selection is best. As was shown earlier, MyPLV provides the weighted profiles to examine the annualized performance for the total plant and for the individual chillers. The MyPLV bid form provides a worksheet to compute a simple payback in years. As before, we will continue with the example of a two-chiller plant in Houston. We are looking at paybacks based on energy use at 10 cents a kilowatt hour. The MyPLV bid form can analyze demand charges with an associated ratchet, but that was not done for this example. But instead of looking at equally priced chillers, we will expand the analysis to a comparison of 6 centrifugal chillers. They are low, medium, and high efficiency, both fixed and variable speed. The low efficiency units perform at about the ASHRAE 90.1 minimum levels. We'll use the weighted profiles provided by MyPLV and use the bid form to generate a simple payback. To perform the analysis, the chiller performance data is entered into the spreadsheet for each of the chiller load and entering condenser water conditions specified. These are obtained from the manufacturer's selection program. Note, we have 6 columns of data to represent the 6 chillers considered. The data is input into the light blue cells with calculations performed below. The payback in years shown at the bottom. Plotting the results, we see the following. This chart details the results for the chiller plant when both chillers are the same. This is the default computational method for MyPLV. The LE, ME, and HE notations refer to low, medium, and high efficiency chillers, with the fixed speed results plotted in blue, the variable speed results in red. The y-axis details the annualized kW per ton, the x-axis detailing the payback in years. If life cycle cost is the goal, the improved performance for high efficiency fixed or variable speed chillers seems to make sense. However, the payback years is getting up there. If the chillers are examined individually, the payback period for a high efficiency variable speed chiller is pretty good for the first chiller. The second chiller, however, appears to favor a medium efficiency fixed speed chiller. Variable speed for the second chiller has a very long payback or none at all. Of course, these results are specific to the electrical costs that were assumed, and some variation is expected with other assumptions. If this is what we find in a relatively warm climate such as Houston, what if we repeat the analysis for Chicago with all the same assumptions? For Chicago, the number of ton hours is greatly reduced as compared to Houston, and therefore the payback can be lengthy for higher performing chillers. Like was done for Houston, this first chart details the payback associated with the various chillers when both chillers in the plant are the same. For this case, any selection beyond a medium efficiency fixed speed chiller becomes a fairly lengthy payback. However, when considering the first chiller, there is a significant amount of low temperature operation and the variable speed chillers start to look good. As we found with the Houston simulation, the variable speed chillers do not provide a good payback for the second chiller. In fact, anything beyond the minimum efficiency fixed speed chiller has a long payback. Regarding the last key point that I was to cover when comparing fixed and variable speed chillers, that is, which is better, a fixed speed or variable speed chiller? I'm going to go out on a limb here and suggest that every plant should be considering high efficiency variable speed operation for perhaps 50% of the plant capacity. However, operating these plants require that the tower be controlled to take best advantage of lower outdoor wet bulb conditions to reduce the lift seen by the chillers. Some type of optimization algorithm needs to be employed to ensure the tower fan power does not get out of control relative to the chiller operation and that chiller or tower limits are not violated. But the real takeaway is that all plants, and for that matter chillers too, operate at different load profiles and one size does not fit all. There are tools such as MyPLV that are available to sort out some of these differences. If you want to know more about the MyPLV tool, it is available for download from the Trane website. Lee, what's next?
With the wider application of variable speed, we are witnessing what I consider to be a disturbing trend, adding variable speed drives to plants and then making the plant configuration and control overly complex, or using system design techniques that were developed to overcome a previous unit or system shortcomings that bring little value in a modern variable speed plant. Those of you who have attended E&Ls in the past probably remember this quote. It's a favorite of ours. I would suggest that complexity is not only the enemy of first cost, but sustainability as well. What we need to be doing is leveraging the performance advantages of variable speed chillers to simplify our chiller plant designs and control to lower their life cycle cost with increased sustainability. The first application option we'll consider is swing chillers. Swing chillers have been a popular energy-saving option for primary-secondary decoupled systems for many years. The Trane Tracer Chiller Plant Control application even has a standard sequencing method for them. The question we need to ask is, with variable speed chillers and variable flow systems, do swing chillers bring value? My answer is no. To see why I say this, we need to understand why swing chillers are beneficial in conventional constant flow primary, variable flow secondary systems. A swing chiller implies an asymmetric plant, one that has one or more large chillers and one smaller chiller, the swing chiller. It is typically sized at half to 2/3 the capacity of the large chillers. It runs at low loads as well as alternating on and off between the larger chillers to provide the plant with more steps of chiller loading and primary chilled water and condenser water flow. There are 3 drivers for a swing chiller. The first is to save primary chilled water pumping energy. It provides smaller steps of primary flow capacity modulation. These small steps reduce the excess flow in the bypass pipe, reducing the non-productive primary side pumping energy. With the rise of variable primary flow, either direct pumped primary flow systems or variable primary, variable secondary systems, the bypass flow is eliminated or greatly reduced under all operating conditions. Therefore, applying a swing chiller to provide small steps of flow change does not apply. This eliminates the first driver for a swing chiller. The second driver is similar to the first, condenser water pumping energy. Once again, large steps of constant condenser water flow result in excess water flow and pump energy use at part load conditions. The use of either more optimized earthwise design flows of 1.8 to 2.5 GPM per ton or fully variable condenser water flow for high design flow systems greatly reduces condenser water pumping power, eliminating the second driver. The final driver for a swing chiller is that the very low load efficiency of constant speed compressor chillers can degrade significantly. Running a smaller chiller at a higher load point can provide improved chiller energy efficiency. With the variable speed modulated compressors we're talking about today, the low load chiller performance can be quite excellent. So the three reasons and benefits swing chillers have provided to traditional system designs in the past are greatly reduced, if not completely eliminated, with the application of one or more variable speed chillers in an optimized variable flow chiller plant. There is also one reason not to use swing chillers in variable flow primary plants. Depending on the various chillers' flow requirements, sequencing different size chillers while maintaining their required minimum flows can be very difficult. The VPF bypass valve may need to modulate quickly and widely every time the chillers sequence for the life of the plant. This puts great stress and risk on the control system. Our advice to maximize the efficiency and simplicity of a chiller plant with a wide load swing is to select at least one equally sized variable speed chiller for low system loads and avoid the complexity and risk of a swing chiller. Another concept tried in some systems is forcing unequal loading of chillers. This scenario goes something like this. A constant speed chiller and a variable speed chiller are online, and the sequence calls for the constant speed chiller to run at its sweet spot load, typically mistakenly thought of as 80%. The balance of the load is passed on to the variable speed chiller, which may then run anywhere from minimum to full load. The idea is that keeping the constant speed chiller in its perceived sweet spot will result in reduced plant energy consumption. But another way to look at this is that by passing on only the balance of the load to the variable speed chiller, the theoretically most efficient chiller very often operates the most lightly loaded, which does not sound like an optimal sequence. Both are simplistic views of the system operation. If you think back to previous charts, both chillers actually have relatively wide efficiency curves, which really drop off badly only at very low part loads. If we apply the principle that any chiller will operate most efficiently when the load and lift decrease together, we would conclude that allowing the chillers to unload equally would be best. Practically speaking, it's also true that the most stable and generally most efficient operating strategy when multiple chillers are operating is to allow the chillers to share the building load equally relative to their design capacity. Beyond the efficiency issue, there is typically significantly increased control complexity involved with trying to accomplish any significant unequal loading scenario. Often, both flow and chill water set points must be adjusted for each chiller on a real-time basis to force unequal loading while meeting the building cooling load and supply water temperature requirements. On systems where this has been attempted, it's often found that times when variable speed chillers are forced to a low load don't correspond to low lift. As a result, this system control scheme will cause the variable speed chiller to operate at a lower efficiency than first thought. In the worst case, it can force a centrifugal chiller into surge. This is not just theory. I've seen it happen on more than one plant. I do feel fortunate that when I've seen this occur, it's mostly been competitors' chillers being punished. But that's not to say that in an extreme case, it couldn't have happened on a Trane chiller as well. And we know what operators do with sequences they don't understand or that cause them issues anytime in the life of the plant. The last application consideration I'd like to discuss is stability of control. Through the years, we've talked about the importance of optimized control to efficient system operation, but that's doubly important for systems with variable speed chillers. We've spent very little time on the subject of stable control. All chillers, but particularly variable speed chillers, benefit from stable system control. Unstable control can take many forms. Constant staging up and down of fixed speed, multiple speed, or even variable speed tower fans, hunting air handler control valves, or a hunting variable primary flow bypass valve. unstable control cycles any chiller through periods of overcooling and undercooling. The chiller must constantly fight against the varying temperatures or flows to meet its main goal, to maintain its leaving chilled water temperature. This not only reduces its operating efficiency, it causes additional wear and tear on all system components. Today's variable speed chiller controls are quite responsive. They will quickly make corrections to the chiller operation with changing system conditions. They are also quite smart. If the system is operating with constantly changing conditions, such that a chiller might be pushed outside its safe operating envelope, it will widen its operating margins. This protects the chiller, but reduces its operating efficiency and control accuracy. Exactly how reactive the controls are and how fast they recover and restore efficiency varies by manufacturer. The bottom line is, if a system design includes a variable speed chiller, it should include either optimized fixed flow or carefully commissioned variable control on the other components in the system, rather than cycling or stepped control. And as much as possible during the commissioning process, for the life of the job, we need to strive for stability of system operation. Mick, would you pull this all together for us?
Let's summarize what we learned today. To accrue significant energy savings from a centrifugal chiller with a variable speed drive, the lift must be reduced. This is usually accomplished by coordinating cooling tower control with chiller control. On a screw chiller with a drive, if either the load or the lift is reduced, significant energy savings can be realized. When performing analyses, always compare options. First, a chiller with a variable speed drive and a same price premium efficiency chiller. Then look at the performance of investing in more heat transfer exchange surface and a variable speed drive. Make sure the chiller performance is modeled correctly and use the actual utility rates, including any demand charges. We discussed Chiller Plant Analyzer and MyPLV, which can be used for preliminary analysis. Those two analysis programs allow you to quickly develop economic information you could present to building owners. From an application standpoint, variable speed drive chillers may cause us to change past chiller plant design paradigms. The use of hot gas bypass to maintain load is not necessary, and since it's so inefficient, should be avoided, no matter what it's called. Since chillers with drives experience reduced energy use when lift and/or load are reduced, past reasons to use swing chillers may no longer be applicable. And finally, when systems are designed, installed, and commissioned, we want them to keep operating stably and efficiently. Simple is good. There are times when we can make the system so complicated that the operators will take control in hand. So many times, complicated sequences that are not well documented or understood aren't used, and the result is more real energy use than efficient, simple sequences. Jeannie, take us home.
Thanks, Mick. There are a number of publications available that provide more information on the material covered today. A bibliography detailing these resources is included in your handout, and it includes an ASHRAE journal article authored by Brian Sullivan. Additionally, all past broadcasts are available on DVD at trane.com/ENL. All are accredited for continuing education, and many are available on demand free of charge. Visit trane.com/continuing education for a complete list to satisfy credentialing requirements, and many are lead specific. And remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your member information to your local site coordinator. And finally, this spring, based on your feedback, we'll revisit a couple of fundamentals and present a discussion on coil selection and how to evaluate sound data. These two will be a little bit shorter, hopefully making them more convenient to attend. And we'll return in fall to discuss small chilled water systems. So please plan to join us. Thanks for your time today. We look forward to seeing you later this year.